I know there's been a lot of excitement for this particular one. Black holes is the subject, and I think that it's really fantastic in this particular case, when I hand the mic over, that we have a former NSSL competitor that's actually participating. So at this point in time, I won't spend any time about events next week. We've done that already, but I would like to introduce Ms. Fisher from Andover High School to actually introduce our guest speaker. And I just want to say thank you for dedicating your time to the league today. And I am personally looking forward to the talk, and I know the students that are present are as well. So Ms. Fisher.
Hi, everyone. Sarah Fisher, Andover High School, and I have the great pleasure today to introduce Dr. Greg Salvesen. As Ms. Fay mentioned, he's a graduate of Andover High School. Sadly, I was never lucky enough to have him in class because he was already sort of an upperclassman by the time I started working there, and I mostly taught freshmen, but we did run into each other in the halls once in a while. And he has since gone on to get his doctorate in astrophysics and has worked in a couple of cool places out in California and currently at Los Alamos Research Laboratory down in New Mexico. So he's doing research on black holes, which is a personal favorite. So I'm super excited to hear this talk. And so over to you, Greg. Thank you so much, by the way, for coming.
Great. Yeah. Thanks, Sarah. Thanks, Tammy. Thanks, Jeff. Very happy to be here. I'm going to pull up my slides now. Let's see if this works. Great. Can I just get a confirmation, yes, that you can see my screen okay and you can hear me all right? Great.
Yes to both.
Perfect. All right. So we'll get started. So my name's Greg Salvesen. I am a former Andover High School graduate, and these days I work on black holes. And so I wanted to share with you guys today some of like the most current research on black holes, really just within the last couple of years. This field has really exploded. And I want to highlight some things we know about black holes and how we know those things, and along the way, reveal some things that we still don't know. All right, so what I'm showing you here, this is in the first ever image of a black hole. It's a black hole in a galaxy relatively close to us called M87. This is not the black hole in our galaxy. And what you're seeing is this bright ring of gas around a dark shadow. And just to give you a sense of scale here, that dark shadow, that black region in the center, that's the black hole. The event horizon of the black hole, and I'll talk about this shortly, is roughly the size of Pluto's orbit around the sun. And so the shadow you're seeing is actually slightly bigger than the event horizon of the black hole. But now this might sound really enormous, like a large spatially extended object. But when you think about it, it's actually something like 6 or 7 billion times the mass of our sun crammed into the size of our solar system. Whereas our solar system only has 1 time the mass of the sun in it, right? So this is a huge amount of mass in a very, very small space. And that's essentially what a black hole is. So our working definition of a black hole, what is a black hole? So at the bottom here, I'm defining it as a region of space-time that is so compact that nothing, not even light, can escape from its surface. And surface is in quotes here because black holes actually don't have a physical surface. And you can ask me about that toward the end of the talk if you'd like. But so what this image is showing is the Tesla that Elon Musk shot off into space, which escaped from Earth's orbit. So by putting it on a rocket and shooting it off the Earth fast enough, it escaped from Earth's gravitational pull. Now, if you made Earth more and more and more compact, just squished it down in size, it would become more and more difficult to launch something off of its surface. And at some point, it becomes so compact that nothing could be launched off of its surface and escape. And so in the case of the Earth, if you took the entirety of the Earth and compressed it down to the size of a marble, all right, then the escape velocity from Earth's surface would be the speed of light. And that's effectively the definition of a black hole. An object so compact that nothing, not even light, can escape from it. And as far as we know, light is the fastest anything can travel. So if not even light can escape, then nothing can escape. And everything interior to the black hole is forever lost, and nothing can ever get out of the black hole. All right. Now, suppose you take a more massive object, like a star. So this is the sun. This is an image of the sun taken about an hour ago. I just pulled it off the web from the Solar Dynamics Observatory. If you took a star like the sun and crammed it into the size of a city, so a city is, a few miles across, let's say, right? If you crammed it into that size, then you would have a black hole. So the more mass you have, the larger the black hole will be. But it's still a very, very, small region of space relative to like the size of the astrophysical object I'm talking about. So, the Earth isn't going to collapse into a black hole, but stars that are roughly 10 times more massive than the sun will. And taking all of that mass and cramming it into a tiny, tiny small space will produce a black hole. All right. So I'm going to go through a list of 3 things that we know about black holes and kind of discuss how we know those things. So the first thing I wanted to talk about is that astronomers think there's a supermassive black hole lurking at the center of every large galaxy in the universe. So every single galaxy has a black hole somewhere between 1 million and 10 billion times the mass of the sun at its center. So I'm going to explain to you how we know that. All right. So this is the Virgo cluster of galaxies. This is actually like a zoom in on the center of that cluster. There's something like 1,300 galaxies composing this cluster. And this one that I've highlighted in this box, that galaxy, it's like the fuzzy thing with the bright center. That galaxy is called M87, and it is the biggest galaxy in the Virgo cluster of galaxies. And that's the one whose black hole I had on the title slide. All right, so now we're zooming into that one galaxy, M87, and here's a series of zoom-in shots shown by the boxes, right? And so, can you see my cursor here or no? Great, okay. So this extended thing here is called a jet. So this is produced by the black hole at the center of the galaxy. So this, relatively speaking, teeny tiny little black hole at the center of the galaxy, which is maybe the size of our solar system, can shoot out this jet of particles moving at nearly the speed of light and extended spatially, comparable to the size of our Milky Way Galaxy. A jet of that size is emanating from the tiny little central region of the galaxy, and that jet is launched and powered by this black hole. So black holes can be very powerful objects if you give them some gas. All right, and so this is the image of the black hole, which you already saw in the title slide. And so this is like a special case. We're actually able to take an image of the black hole in this galaxy. And partly that's because the black hole is so massive. I think I mentioned already that the black hole at the center of this galaxy is something like 6 or 7 billion times the mass of the sun. That's a real whopper. And because it's so big, its spatial extent on the sky is big enough that we can actually resolve it with, I'll say, a quote-unquote telescope. Oops. And I'll explain what that means in just a second. Okay, so this black hole at the center of M87, the name of the black hole is M87 star. And again, what you're seeing here is gas, like the bright stuff is gas very, very, very close to the black hole and moving at incredibly relativistic speeds. And the brighter region is gas that's coming toward you, and the redder regions are gas that's moving away from you. Now, if we had a telescope with incredibly good infinite resolution, what might we see? Well, you can, on a computer, on a supercomputer, you can ask those kind of questions and simulate what gas around a black hole looks like. So this is just a supercomputer simulation. And what astronomers have done is they'll run many of these simulations, which account for general relativity and radiation and hydrodynamics, how the gas moves around, and magnetic fields. All of that stuff is included in these simulations. And you can change properties of the black hole, like how massive it is or how fast it's spinning. You can change properties of the gas orbiting the black hole, like is it inclined relative to our line of sight? And astronomers will run grids of these computer simulations and try to compare them to the observation, which is this, which doesn't have perfect resolution. And the hope is that by comparing these computer simulations to what you actually observe, maybe some of those computer models gain favor relative to others. But right now, the resolution of the black hole image is not, it's amazing that they're able to do this, right? But it's maybe not quite good enough yet to definitively rule out or favor certain computer models over others. All right, so how did they, just very briefly, how did they make this image a reality? So it turns out the resolution you're able to achieve with the telescope depends on how big that telescope is. The dish size of the telescope dictates how small of an object you're able to resolve on the sky. And through very clever technique called very long baseline interferometry, astronomers are able to effectively create a telescope that's as big as the entire Earth. And they do this by having lots of telescopes distributed all over the Earth. That's what all these different dots are. And as the Earth rotates, it sort of gives you access to more and more area of the Earth, and you're able to combine all of these different observations in a clever way to effectively make lots of individual small telescopes combine together and act as though they were one giant telescope. And the more sites you have spread all over the world, the finer and finer resolution image you will get at the end of the day. And so this is something that is a really hot topic right now, is this team called the Event Horizon Telescope Collaboration is incorporating more and more telescope sites to improve upon that kind of image that they took of the black hole in M87. Now, that same team also pointed all those telescopes at the center of our galaxy, the Milky Way, because our galaxy also has a black hole at its center, but those results haven't been released yet. There is, speculation that those results will come out any day now, but we'll just have to wait and see. Okay, so now I'm showing you an image of our Milky Way galaxy, and that this center bit here, this is the galactic center, and that's where the supermassive black hole at the center of our galaxy is. Now, we can just take a picture of it, but like I said, that hasn't been released yet, but people are working on it. But there are other ways we can measure the mass or observe the black hole at the center of our galaxy. And this work actually just won the Nobel Prize in Physics last year. And it was work led by a professor at UCLA. Her name's Andrea Ghez. And I think she was the 4th woman to win a Nobel Prize in Physics. So this movie is showing you how they did that. So what they do is, over a period of decades, they track the orbits of stars at the center of the galaxy. And they just look at the paths that those stars take. And as they, start to complete a full orbit, they can track those trajectories and notice that they're orbiting something very massive, but something that is dark, something that's not producing light. But even though they can't see the thing that is being orbited, based on orbital dynamics calculations, they can work out what the mass of that thing being orbited is. And it turns out the mass of that thing is something like 4 million times the mass of the sun, which again, as far as supermassive black holes go, is kind of wimpy. It's still a crazy big number. And because that 4 million solar masses is contained interior to those orbits, they can say that that is so compact that it has to be a black hole. Remember, I was saying earlier, if you took the Earth and crushed it to a marble, it has to be a black hole. Same kind of thing here. If you took 4 million times the mass of the sun and crushed it to be interior to one of those orbits, it has to be a black hole. And so that was really the first definitive evidence for the existence of a black hole, were these observations. So how did they actually make those observations? It's really incredible. So there's a pair of telescopes on Mauna Kea, which is a mountain in Hawaii on the Big Island, and the summit is at about 14,000 feet. And this is a picture of me up there. I hiked up there once, and with my fingers, I'm showing the Keck Observatory. So it's a pair of 2 telescopes. Now, when you're observing something at the center of the galaxy, you're like really, really zooming in. And so you need exquisite resolution. But the trouble is, like, when you look up at a star, you notice that a star twinkles, right? And the reason that a star twinkles is because its light has to pass through our atmosphere, and our atmosphere is turbulent. If you've ever been on an airplane, you probably know this. It's not always smooth sailing. And so that light can get sort of deflected around, and its appearance isn't rock steady. It twinkles and it changes a little bit. Well, that's a problem because it makes your images blurry. This isn't an issue if you have a telescope in space, because then you're outside of the atmosphere and you don't have to worry about this. But here on the ground, you do. And so what Keck does to get around this is something called adaptive optics. What they'll do, they'll shine a laser at a star that they already know about. Like, they know that this star does not vary over time. It has a predictable behavior. It's known as a reference or guide star. So they'll shine the laser at that star and track it, so they know what that star should look like. And as they observe that star, they're simultaneously observing a star that they don't know what it should look like. And so when they look at the star that they say, I know this star should look a certain way, okay? And as that light gets distorted by the atmosphere, they then know, oh, okay, those distortions are because of atmospheric turbulence. And then they can literally use that information to change the mirror on the telescope, to actually deform the mirror in such a way to apply corrections for turbulence in the atmosphere. It's really an incredible technique. And so what I'm showing now is the result of that technique. So this is the image you would see without using this adaptive optics technique of the galactic center. If you turn this adaptive optics on, suddenly all that blurriness fades away, and you can just nail down what these stars, like the spatial resolution just dramatically improves, all right? And so this is sort of the state of the art right now of this technique, but they're working on making it even better. So this box that I'm showing you here, all these stars are in this box. If we zoom in to a box this size, that's what I'm showing you now on the right. And what this is now the image you would see with no adaptive optics. So this is called seeing limited. That just means all the turbulence in the atmosphere is mucking up your image and making it blurry. If you turn on adaptive optics, like the current capabilities of it, this is what you would see. But the next generation of adaptive optics predicts you should be able to see something like this. So they're continuing to improve this technique, and it's just going to get better and better and better to make these kind of measurements of stellar orbits around the supermassive black hole in the galactic center. Okay. All right, but this is just, I've only showed you 2 black holes so far, right? The one at the center of our galaxy and the one in M87. And they can make these kind of measurements using similar techniques, not imaging the black hole, but using techniques where you're measuring the motion of stars or the motion of gas. You can measure the mass of the black hole at the center of a galaxy. And so every one of these data points is a measurement of that black hole mass at the center of a different galaxy. And so the y-axes are showing the mass, the black hole mass measurements, and the x-axes are showing 2 different properties of the galaxy. On the right here, it's the luminosity of the galaxy, how bright it is. And on the left here, it's what's called the velocity dispersion of stars in the bulge of the galaxy. The point is that there are strong correlations, like you can fit a line between these quantities. And what that suggests is that there's some fundamental connection between supermassive black holes and properties of galaxies. So it seems like supermassive black holes go hand in hand with galaxy formation and evolution. So even though we only have a few tens of direct measurements of black hole masses at the center of galaxies, the thought is that all of these galaxies are more or less not special. And so astronomers extrapolate this idea to all of the galaxies in the universe and say that, we expect essentially all galaxies in the universe to have a supermassive black hole at their center, because it seems like supermassive black holes kind of govern galaxy formation and evolution. But maybe take that with a grain of salt, because there are a lot of galaxies out there. And again, we haven't directly measured the mass in every single one of these galaxies, far from it. This is the Hubble Ultra Deep Field. So for 11 days, the Hubble Space Telescope stared at a tiny little patch of sky, really tiny. Like if you took your arm and held it out and held onto a penny, and you looked through Abraham Lincoln's eyeball in that penny, that's the size of the patch of sky that I'm showing you. It's teeny, teeny, tiny. And Hubble stared at that for 11 days and out popped something like 10,000 galaxies. So every point of light you see in this image is a galaxy. And astronomers think that at the center of every one of these galaxies, there's a supermassive black hole. Okay, I'm going to skip this in the interest of time. All right, so the next topic, or the next thing we know about black holes that I want to take you through, is that they form when a massive star dies. All right, so what I'm showing you on the left is what's called a supernova remnant. So a supernova is when a star explodes, okay? Now, this one is especially spectacular. It's called the Crab because it happened in our galaxy in the year 1054. And we know that it happened in the year 1054 because there are records of this event happening in China and a handful even in North America. This pictograph I'm showing you on the right is, gosh, it's maybe like 3 hours from my house in northwestern New Mexico, where Native Americans observed and recorded this supernova event. So this drawing, this star represents the supernova, which would have been about as bright as Venus and visible during the day for about a month and visible in the night sky for about 2 years with the naked eye. And then this is the moon, and the position and phase of the moon, the phase of the moon and its position relative to the supernova line up with what would have actually been observed, and the handprint marks that this is a sacred site. And you can't tell, but this is actually on a ceiling. Anyways, the point being, a star explodes in a supernova event and produces this supernova remnant as that explosion propagates outward. Now, the thing is, though, these events can leave behind either a neutron star or a black hole. In this particular case, a neutron star was left behind, not a black hole. A neutron star is also very, very compact, but it's not quite a black hole. And we know this one left behind a neutron star because we can see it. And here it is. At the center of this supernova remnant is what's called the Crab pulsar, which is a rapidly spinning neutron star. Okay, but sometimes the thought is that these supernova events leave behind black holes. Now, how do we discover these black holes? Well, we have to get kind of lucky because a black hole just hanging out by itself isn't going to emit any light. And so we don't have any really easy way to find a black hole like that. But if the black hole is in a binary system with another star, and that binary system is very tight, or that is to say, the black hole is very close to that star. And I mean really close, like as close as Mercury is to the sun. Sometimes those kind of systems go into outburst and get very bright for a short period of time. And we observe that brightening in X-rays. So we have X-ray telescopes in space, and those telescopes observe this sudden brightening event. And then through similar dynamical measurements, we can, look at these systems, take data, and work out that the black hole at the center of this disk here, or the object at the center of this disk here, is greater than 3 times the mass of the sun, in which case it has to be a black hole. And this has to do with properties of matter and upper limits for the mass of neutron stars. So if we can find these systems, then we can find black holes that we think were produced in the collapse and explosion of a star. And I should, just as a quick side note, binary systems are very common in astronomy. So the thought is that most stars are actually part of a binary system. Our sun is not. But what this means is, like, when you look at a star in the night sky, chances are that it's actually two stars. And they're just so close together that you can't visually separate them by eye. But that's just sort of a neat thing that kind of always struck me, is that, you know, you're looking at a star, but chances are it's two stars. Okay, so how do you form one of these black hole binary systems? Well, here's the thought. You start off with two stars. I'm showing you this like red star and blue star, and they're far away from each other, all right? Don't worry about the arrows right now. I don't think I have a whole lot of time to get into it. So just don't worry about the arrows. One of those stars starts to reach the end of its life and swells up, gets really, really big, like 1,000 times bigger than it was. And that envelope of the star engulfs the other star. And so now they can exchange energy and angular momentum. And what that does is it shrinks their orbit. And so they're getting closer and closer and closer. And at some point, all of that orbital energy that gets dumped into this envelope causes the envelope to blow apart like that. So now you're left with the core of an evolved star, that's this red guy, and your other regular star, the blue guy, okay? Now, sorry, don't worry about the spins here, right? Okay, so now this star explodes as a supernova and leaves behind a black hole. All right, now here's a really cool thing. We can look at systems like this, where you have a black hole and a regular star in a binary orbit, and we can just focus on the regular star and do what's called spectroscopy. So we measure the spectrum of this star, and that's something I'm showing you here. And I know this is a bit of a complicated plot, but let me just take a little bit of time to explain it. So what I'm showing on the x-axis is the wavelength of light that we see coming from this star, okay? And on the y-axis, it's how bright, or, you know, the flux of that light, or how much light you observe at that wavelength. Now, depending on the composition of the gas in the envelope of that star, for instance, if it has iron or silicon or titanium or magnesium, calcium, whatever elements are there and how much of those elements there are, that will imprint these dips, which we call absorption features. So like here's a big dip from calcium, all right? Now the how deep this dip is set by how much calcium there is in the star. Now, the black line is showing the observation, all right? That's what's observed in one of these stars. The blue line is just a model fitting that observation. And that model, you know, has things baked into it, like how much iron there is, how much titanium there is, how much magnesium there is, whatever. Now, the yellow line is showing what you would predict there to be, what you would predict this spectrum to look like if the composition of the star was that of a normal star of its type, all right? But what we see is that there are these big dips that the yellow line doesn't agree with, but this blue line does agree with. And this blue line is telling us that there's a lot of heavy elements, things like iron, magnesium, silicon, in the atmosphere of this star. And so how did those elements get there? Well, the idea is that when that supernova happened that formed the black hole, it blasted this star and enriched it with these heavier elements that have no way of being there otherwise. So by observing a large abundance of this material, you can conclude that it's indirect evidence that the black hole was produced in a supernova event. Okay. Another piece of evidence we have that supernova produced black holes is when this collapse happened, it might not be perfectly symmetric. And it might impart what we call a kick to the black hole and send it careening off somewhere. But if that kick is not too extreme, the orbit will remain bound, and it'll just, we'll ignore this, and then it'll just careen off into space, okay? And what we observe, I'm showing you now the distribution of these kind of black hole systems in our galaxy. And you can see they're kind of all over the place and moving all over the place. What you would expect is that most stars lie in the plane of our galaxy, like this horizontal line that I'm drawing out here. Most stars lie in that plane, but none of these black hole systems are there. They're floating around elsewhere, and they're moving with kind of strange velocities all over the place. And the way that they got there is an asymmetric supernova collapse sent them careening off some way. And so this is another piece of evidence that supernova produce black holes. Okay. Now, the last topic I wanted to touch on is that two black holes can merge together to form one bigger black hole. And this is really neat, cutting edge stuff. So this is a computer simulation of
Looks like Greg's computer has frozen up or something. He mentioned at the beginning of the talk that his desktop computer sometimes had some problems. So he said we should sit tight, and he'll rejoin the meeting and pick up where he left off.
I think this is some of the coolest imaging. I just am amazed at how far we've come and our ability to capture images of space. It just makes me excited.
Yeah, it's pretty awesome.
Here's Greg again. Let me unmute him. Whoop.
Sorry about that. My computer, that simulation was too much for my computer to handle.
So it let out all the magic smoke, huh?
That's right. Okay, I think I can be back up here.
Okay.
All right, can you see my screen?
Yes.
Great, sorry. We'll pick up from where we left off. All right, so this is a computer simulation of two black holes merging together. And these kind of simulations are really hard to do because the black holes distort space-time, and you have to account for that in your simulations. So this is really a cutting-edge thing. Most simulations, you don't have to worry about the background space literally changing, but in these kind of simulations, you do. Right. Okay, so that's a computer simulation. And this is showing another computer simulation or representation of the gravitational wave signal emitted by two merging black holes. And you saw that right when they merged, there was this burst of gravitational waves. Okay, and incredibly, that is now observable. And what I'm showing you here is the first detection of a black hole merger made with a gravitational wave observatory called LIGO. So they have one in Oregon and one in Louisiana, and they both observe this event at the same time. So they know it's, not a fluke. That's why they have two detectors. And what you're seeing on the x-axis is time. So it's about a half of a second in time. And on the y-axis is frequency of the gravitational wave signal. So as those black holes get closer and closer and closer, the frequency of the gravitational waves increases until they then merge together and stop producing gravitational waves. So to date, there are many black hole merger events that have been observed, and even some neutron star mergers, and I think even one neutron star black hole merger. And these are revealing all kinds of puzzles and really interesting stuff. So for instance, something that has been a puzzle for a very long time now is, again, sorry, what I'm showing you here are lots of different observations of neutron stars, which are shown in yellow, black holes that were discovered not from gravitational waves, those are shown in purple, and then black holes that were discovered from gravitational waves, those are in blue. And on the y-axis is the mass of these objects in solar mass units. So the highlighted band I'm showing you shows that between 2 and 5 times the mass of the sun, there aren't really many objects there. And that's always been kind of a puzzle, but now astronomers are starting to find some. There are a handful in that, what's been called the mass gap. And another puzzle is that all of the black holes we've discovered before, like before gravitational waves were possible to observe, all of those black holes we discovered before were less than about 20 times the mass of the sun, but the vast majority of the merging black holes we're discovering are much more massive than that. And that's still a big puzzle. And then there's even a further mystery, which is theoretical predictions tell us that black holes shouldn't be produced from, like a star shouldn't be able to produce a black hole more than about 52 times the mass of the sun. Yet we're observing black holes more massive than that are merging together, that were presumably formed from the collapse of a star. And so these are all still big unknown questions in astronomy. And the final 2 slides I have, and the final thought I want to leave you with, is that black holes, something that my mom asks me a lot, and she's on this Zoom meeting. She says sort of like, how is any of this practical? Or how do black holes affect my life? That kind of question. Well, it turns out that many of the elements that are absolutely essential for life are directly related to the production of black holes. So this is the periodic table, and it's doing like an inventory of every element in the periodic table and saying what produced that element. And so what I want to focus on are the elements in yellow, which form from a massive star exploding, and that leaves behind a black hole, okay? And that's quite a lot of elements here. And the elements in purple, which are the result of 2 neutron stars merging together, which leaves behind a black hole. So as strange as it may sound, I contend that life as we know it might not be possible without black holes. But then on the flip side of that, it's possible, although there's no definitive evidence for this, that black holes can cause mass extinction events on Earth. There used to be a theory that something called a gamma ray burst, which is when a massive star collapses. That's what I'm trying to show you here. And it produces an incredibly collimated beam called a jet. When that happens, if that jet happened to be pointed right at you, and it happened fairly close to you, so like if one of these gamma ray bursts happened in our galaxy, and that collimated jet happened to be pointed at us, that would be a mass extinction event, and there's almost no way to predict it in advance. It used to be a theory that that's what killed the dinosaurs. We now know that's not the case, but there have been other mass extinction events throughout history, and this is always an idea that astronomers float out there, is that perhaps a gamma ray burst was responsible for that. So, while black holes giveth, black holes may also taketh away. So that's all I have for you, and I'm definitely open to taking any questions that people might have.
I actually have one. So I was curious, you talked some about how the black holes formed from dying stars. How do the ones in the centers of galaxies form?
That's a great question. So how do the black holes at the centers of galaxies form? So there's sort of two schools of thought here. One is that you formed some monolithic, humongous black hole at one point in the past and fed it with gas very fast and grew it that way. Another idea is that when galaxies merge together, the black holes at their centers will then merge. And so you can have these successive merging events. And the nice thing is these two different predictions, which are what's called direct collapse black holes, that first scenario I talked about, and the black hole mergers scenario, they make different predictions for the distribution of black hole spins. So if you can confidently measure the spin distribution of black holes at the center of galaxies, then you might be able to distinguish between these two ideas. But right now, I mean, people do this, right? And there are claims out there favoring one scenario over the other, but there's no consensus yet. But right, there are generally two ideas. Either lots of mergers produce this massive black hole at the center, or some like monolithic seed black hole that then can feed on gas very quickly.
That's cool.
So it looks like Pascal Moon has raised their hand. So go ahead and let us know what your question is.
It goes when it's being sucked into a black hole, because the law of conservation of mass and energy states that matter cannot be created or destroyed. And if matter and mass keeps getting sucked into black holes, do we know where that goes or how that is redistributed within the universe, if that makes sense?
So I'll see if I can field this and tell me if I don't answer your question. But you're asking essentially what happens to stuff that falls into a black hole. So black hole interiors is kind of the realm of hardcore theoretical physics, but the thought is that everything is destined for the singularity at the center of the black hole. What happens there, nobody knows. It's sort of where like quantum mechanics, like the extremes of quantum mechanics meet the extremes of gravity. And there's no like theory for that yet, really. But the thought, like something that enters a black hole can never get out. And the other kind of interesting thing is that black holes have no defining characteristics aside from their mass and their spin or their angular momentum. So no matter what you make the black hole out of, if I make a black hole out of gold, let's say, all right, and that black hole, let's say it has no angular momentum, no spin, and it has a mass that's, I don't know, 100 pounds, okay? If I also make a black hole out of garbage that has no spin and is also 100 pounds, and then I asked you which black hole was made from gold and which black hole was made from garbage, you'd have no way to tell me. They are indistinguishable from each other. It doesn't matter what they're made of. It just matters how much mass and how much angular momentum get dumped in there. Does that answer your question?
Yeah, that does. And actually that brings me to a follow-up question I just had.
Sure.
What exactly happens to the identity of the elements themselves when they go into a black hole? Because you said you would not be able to distinguish between the black hole of trash and the black hole of gold. Does the fundamental nature of each element change or no?
Well, so as you get closer and closer to a black hole, so these disks of gas that I showed you around black holes, they're very hot, like 10 million degrees. And so before that gas enters the black hole, it's almost completely ionized, right? So it's just made up of electrons and nuclei. But then once that crosses into the black hole, again, I'm not sure I'm going to be able to give you a satisfying answer. At some point, everything is just crushed down to the center of the black hole, and sort of, I guess you're asking what happens along the way, and I just am not going to be able to tell you. Although something I can tell you is that perhaps counterintuitively, like the more massive the black hole is, the less extreme things are when you cross the event horizon. And so what I mean by this is like, the event horizon isn't some special place where something insane doesn't necessarily happen at the event horizon. So if you fell into the black hole at the center of our galaxy, or any supermassive black hole, you would survive crossing the event horizon. Like the gravitational forces you experience would not be so overwhelming as to rip you apart or make you pass out. That would happen later. But the moment you cross the event horizon, that would not happen. But yes, at some point, I mean, gravity wins and everything is just crushed into one tiny spot is the idea.
May I ask one question? My question is, for example, I heard about NASA that for some billion of years, Andromeda Galaxy and our galaxy Milky Way will collapse to each other. What will happen to black holes in center of them? Will they collapse too or not?
So the question is, when the next closest galaxy to us, Andromeda, collides with our galaxy, the Milky Way, what will happen to their black holes? So yes, the thought is that our galaxy will, I think it's like 6 billion years into the future or something like this, collide with the Andromeda Galaxy, which also has a black hole at its center, like ours. So the interesting thing is that like the stars themselves are not going to crash into each other because they're so far apart compared to how big they are across. the gas will get mixed up. It's sort of like, you know, if you had a handful of pebbles and someone else had a handful of pebbles and you threw them at each other, you're both going to get a face full of pebbles because they'll just pass through. So that's like the stars. Whereas the gas is like if you had two hoses pointed at each other, those hoses will kind of mix together. Now, what about those two massive black holes? Well, eventually those black holes will make their way to the center of this new galaxy that's formed from the merger of the two. But it takes some time to do that. And it happens through something called it's modeled as like a friction. It's a gravitational friction where the gravitational forces exerted on these black holes by the collective stars in the galaxy will eventually cause these black holes to sink down to the center. And eventually those two black holes will merge. The problem is that can take a very, very long time. And this is, you know, one of the reasons that people are skeptical of that theory I mentioned earlier of black hole mergers building up an incredibly massive black hole. Because it just takes some time for those black holes to sink down to the center and merge together, but eventually they will. So yeah, to answer your question, those two black holes will eventually merge together at the center of this new galaxy. And people have even found, like there are observations of what looks to be like a weird looking galaxy that seems to be the merger of two galaxies. And at its center, there are two black holes on their way to merging together.
I have another question. So I heard from some of NASA scientists that said that not only black holes can exist, that the white hole can exist too. That like black holes are taking everything like inside, but the white holes exist. They are releasing the energy out. Is it kind of true, or just some stories?
So there's certainly no observational evidence for this. And again, this is one of these things that I think is in the realm of theoretical, like hardcore theoretical physics, as opposed to like astronomy. Gosh, I can't even remember what a white hole is supposed to be, to tell you the truth. There is some, so for instance, there's like an upper limit to how fast a black hole can spin. But this is just an imposed upper limit, because if the black hole were spinning any faster, you'd have what's called a naked singularity. And those kind of things are considered unphysical. You know, they kind of come out of mathematics or something like that. And so astronomers tend to like ignore those kind of solutions where you like divide by 0 or something weird like that. Right. And at the moment, things like white holes and naked singularities exist in the realm of theoretical physics. And I guess I'll just, that's all I can really say about that, I suppose. There's not been any observational evidence for that kind of thing.
I guess I have another question.
Sure.
So for years, I have been, you know, because teaching chemistry, I've always been fascinated with the link between astronomy and chemistry. and the fact that all of the cool elements that I get to play with come from stars exploding for the most part. And then, so for years, I was always, telling my students that the heavy metals were generated from supernova explosions, explosions of supermassive stars. And now it looks like the evidence is leaning more towards those heavy elements being produced through merging neutron stars. I guess I'm just kind of curious about when did they start to put this together? Because that's A,
Sure.
extremely cool, and B, somewhat new information to me.
Yeah. So I guess I don't know how long this kind of thing has been known. I think probably a while, but it hasn't been confirmed like with observations until very, very recently.
Okay.
With the merger, the neutron star merger event. The trouble, it's a very good question. The trouble is that you can only produce up to iron and nickel in the core of a star, okay? Now, to produce anything heavier than that requires processes involving the capture of neutrons onto an atomic nucleus. And so you often, so for the very, very heavy elements, like, atomic number 40 plus, and this is what, so this is what happens with the neutron star mergers. Two neutron stars merge. And so now you've ejected all of this incredibly neutron rich material, and it's still pretty dense. And nuclei can accept neutrons. It's something called R-process nucleosynthesis. The R stands for rapid. So neutrons rapidly accumulate onto a nucleus, and they can then decay into a proton and emit an electron and something called a neutrino, I think. But when that neutron decays into a proton, you're now changing the atomic number, right? Because it's the proton number that dictates what element you have, whereas the number of neutrons you have just dictates the isotope. And by just like cramming neutrons quickly onto nuclei, those can then get transferred or decay into protons and form new heavier elements. But the way you have to do that is to just bombard nuclei with neutrons very fast. Otherwise, radioactive decay happens, and you can't produce these heaviest of elements. I don't know if that's a great answer, but.
Well, I just think it's, I told my kids for years that one of the coolest things about wearing jewelry like a gold earring is that you're wearing a piece of a supernova. And now apparently I need to change that to, merging neutron star, which, to be perfectly frank, is even cooler than wearing a supernova.
Yeah,
so,
for sure.
It's just fascinating to me how this all works.
Yep, totally. And some elements are only like synthetic or man-made, right? So all the ones shown, I think all the ones in brown, none of those are naturally occurring. Well, I should say, like, they all have incredibly short half-lives or something like that. And so they don't stick around long enough to accumulate and be found on the Earth in large quantities. So instead, they have to be produced in the lab.
Yeah, I read somewhere that there's less than 20 grams of francium on Earth at any one time.
Wow.
Because it decays so rapidly.
Yeah, like whatever this element is, TC, I don't.
Technetium.
Okay, so that one like has been observed in the spectrum of stars. or supernova or something like it's been observed astronomically in a transient event, in an explosion. So it's produced, right? But it just doesn't stick around very long. I think, I forget what its half-life is, but it's depending on the isotope, it's going to have different half-lives for different isotopes, but it's very, very short compared to like the age of the Earth or something like that. But yeah, like gold, for example, here, right, atomic number 79, some of it is produced in supernova, but that's right. Like the vast majority is from merging neutron stars. So if neutron star mergers didn't happen, which looks like it accounts for like 90% of all gold, gold would be a lot more expensive because it'd be a lot more rare.
So yeah, it looks like iridium's almost entirely produced in merging neutron stars.
Okay, we have another question from Sophia.
You may or may not have already mentioned this, but why is the glow around the black hole orange? Could other black holes have certain other colors?
That's a great question. So I showed this picture of a black hole, and it looks, orange. But actually, you wouldn't be able to see this. The orange is, this is not what you would see. So what these telescopes are observing are radio waves whose wavelength is 1.3 millimeters. And that is light that you can't see with your eyes. So it's not in the visible band of the spectrum, okay? And so what astronomers do, they say, like, how can we visualize this? They can collect the light, all right, at 1.3 millimeters. And they say, like, we're going to map how much light we collect to a color. So what they're saying is, like, all right, if in this spot on the image, we don't collect a whole lot of 1.3 millimeter light, we're going to make it red. But if we collect a lot of 1.3 millimeter light, we're just going to make it yellow. So it's totally made up. It's just a made up color, but it corresponds to how much of that 1.3 millimeter light they observed. So it's meaningful, right? Like this color scale is telling you, this area is much brighter than this area, but the choice to make it this color is entirely arbitrary. And it's not what you would actually see with your eyes, because our eyes can't see radio light. But yeah, that's a really good question.
So that would be analogous to the colors on a weather map that's generated by a computer, where the colors show the intensity of, say, a storm.
Yeah, sure. Mm-hmm. And same goes for like this image. I think this image is like this background image here is in infrared light. So our eyes don't see infrared, but you put on infrared goggles and you see someone's like body heat, you know what I mean? It's sort of the same idea as that.
All right.
Are there any other questions?
Maybe I'll say this. I want to give a special shout out to the students that have they put your hands up and you've asked your questions today. I'm really proud of you because it's not easy to do. So today has been fantastic hearing your voices. and asking Greg specific questions. It's been great. So if anybody else out there, I'm trying to give you that push to do it, or put it in the chat, because you're doing a great job.
And for me, this is the most fun part. So I really like your questions, and I don't know the answer to all of them either.
That's the fun part about science, right? The not knowing and the trying to figure it out. I have to say, I'm simply blown away by the computer simulations. Those are amazing.
Yeah, these are a big deal. This is sort of, I would say, since I started doing astronomy, maybe, I guess I didn't talk a whole lot about this, but I started maybe my sophomore year of college getting involved in astronomy research. And since then, things have really noticeably changed, because supercomputers have got to be so powerful now. And like now the big shift in computing is actually toward away from CPUs and toward GPUs, which are graphical processing units. And this is largely driven by the gaming industry. So I'm not a gamer, but like, a lot of money is invested in producing like really powerful GPUs for gaming purposes. And astronomers and scientists in general are trying to take advantage of that. So they're rewriting all their computer code to be compatible with GPUs, because there are supercomputers now being built out of GPUs instead of CPUs. And so scientists are having to completely like rethink how they're doing computing.
That's cool. So I have a question, Greg, and it's not directly related to your actual presentation, but from my understanding, there'll be a new telescope that will be sent out into space and hopefully producing more images in maybe, I don't know, April of 2022. But is that going to be something that's going to be useful for the work that you folks do in providing, since it will not replace, but the Hubble has been great.
Oh, so you mean James Webb?
Yes.
So James Webb Space Telescope, last I checked, was slated to launch on Halloween of this year, maybe?
Yeah, I think
We'll see if that happens. It's notorious for being delayed and having problems. But yeah, so something that JWST will achieve, and something that we're all looking forward to, is looking back to the very, very early universe and getting a handle on how things looked back then. Looking back incredibly far to look at things like the very first galaxies that ever formed and the very first stars. And, like the early evolution of galaxies and that connection to black holes.
Okay, I see two more questions, one from Sophia and then one from Jack after that. So Sophia, go ahead.
So I'm really curious about the whole spaghettification process. First of all, is that the real term for it? And two, how does it work inside a black hole?
Yeah, so that is it. So I alluded to this briefly, which is probably why you asked about it. So spaghettification is the technical term for being tidally ripped apart by something. So actually, there are events called, all right, let me step back because you're getting me excited. Okay, so what is a tidal force? So the moon tugs on the Earth, and this is what produces tides, like on the ocean. Okay, now when the Earth has some size to it, and so the moon tugs on the side of the Earth that's closer to it more than it tugs on the side of the Earth that's further away from it, because the force of gravity is stronger the closer two objects are. So one side of the Earth is being tugged on a little harder than the other side. And so what that's doing is kind of stretching, right? Now the Earth is made of like rock and stuff like that, so the Earth isn't deformed. But if that tidal force was stronger, so if the tidal force is just like the difference between the force on one side of something and the force on the other side of it, all right? And there are events called tidal disruption events where a star gets too close to a black hole, that the black hole shreds the star apart through a tidal force. And so that star is spaghettified. If you were to fall into a black hole, let's say you fell like your toes first and then your head through the event horizon. Those are closer to the singularity. They will experience a greater force than your head, and you will be stretched out like a strand of spaghetti. That's where it comes from, okay? Now, I forget like what kind of G-forces your body can withstand in that position, like pencil dive position, but it's not as much as your body can withstand from front to back. So if you wanted to survive falling into a black hole, it's best, I mean, you're going to die, because if you wanted to survive for the longest amount of time, it's best to do like a belly flop, because your body, and they know this because there've been like, you know, experiments on test pilots and things like that about how much G-forces your body can withstand. But it's best to go belly flop, because your body can withstand G-forces that way much better than pencil dive. And actually, where is it? The reason this image, so like, you see this star is kind of teardrop shaped. Can you kind of see that, right? That's because of a tidal force that the black hole at the center here is exerting on this star. So the black hole is pulling on the star harder on this close bit, and gravity is less strong further away. And so that is distorting the star into this oblate shape. It's a tidal force. It's the same thing that the moon does to cause the tides on the Earth.
Okay.
That's kind of rambly, sorry.
That's okay. And Jack has a question.
Yeah, going back to the simulations and how you're talking about how they're using GPUs and the supercomputers to make these work. To actually generate the simulations, are they using like an engine of some kind that would be similar to like a game or a render engine, or is it a different system entirely?
Gosh, I don't even know what you're asking, because I just don't know enough about computers, I think. Could you ask that one more time, please? It's not on you, it's on me, I promise.
Yeah, so what I'm just wondering is, like, to generate these simulations, are they using like a more complicated, more accurate version of like a game engine or a render engine where they can set parameters and then it'll simulate what plays out? Like if you put gravity simulated into a video game, or is it a different system where it doesn't work in the same way to get that result?
I understand your question now. Thank you. That's an awesome question. So like in the games you play, when you turn on gravity or something in your game, it's not doing a physics calculation. It's like making a big approximation for how gravity acts. So like these science codes are like calculating the correct equations without the kind of approximations that are done in video games. So like a video game, you shoot something, I don't know, and it follows some trajectory, or you jump off of something and you fall at some rate and you're, you know, accelerating. in these video games, all that kind of stuff is generally not calculated correctly. It's approximated so that the calculations can be done quickly. In science codes, it's important to be right. And so these calculations are done without those approximations. Does that answer your question?
Yeah, so it acts more like a highly accurate render engine where it's taking the actual equations.
That's right. Yep. And solving those equations, that's sort of what the whole game is about. How can we efficiently solve these equations that are expensive to compute? Expensive meaning like computationally expensive. Because you want to get the physics right, but it takes a lot of computing power to do that. Whereas like in a game, you just want it to kind of be fun, and look goodish.
There. Okay, we have a question from Pascal.
Hi. So, I know Hawking's radiation is a thing, and I know a little bit about it, but do you mind explaining it a bit more, since the concept's still a bit fuzzy to me?
If I'm being honest, the concept's a little bit fuzzy to me too. So this idea is that over an incredibly long period of time, like ridiculously long period of time, black holes can eventually evaporate because they possess some meaningful temperature. And so they are radiating, albeit at a very, very low, undetectable level. And again, this is not something I have a good handle on. And it's also kind of in the realm of the theoretical physics stuff that I don't know very well. But the thought is that over an incredibly long period of time, and I mean like the ultimate fate of the universe kind of thing, like at some point, like the universe, so right now the universe is expanding, that expansion is accelerating. And so stuff is getting further and further and further away at a faster and faster and faster rate. And at some point in the future, that rate will beat out gravity. So even like right now on small scales, gravity still can beat out this expansion. So we have like clusters of galaxies and things like that. But at some point, that won't even be possible. And stuff will have expanded so far and be so isolated. And all the stars in the universe will have died by that point. And the only thing left will be these evaporating black holes, which over some insanely long period of time evaporate through Hawking radiation. I wish I knew more, I'm sorry.
Okay, and Pascal, you have another follow-up question. Go ahead.
Yeah, thank you for that. That explains things a little bit better, I guess. But I have another question which is sort of unrelated on a different topic. And so how did you personally begin to discover astronomy and your love for it? Like, did you have any single point in your life that inspired you?
Yeah, that's a good question. So I'm not one of these people who like has always been into astronomy. You find a lot of those kind of people who are astronomers, but like I've never even owned a telescope in my whole life. I've never even been to a telescope to observe, because all the telescopes I use are in space. But for me, I had a really good physics teacher in high school. His name was Dr. Francis, and he was just awesome. And everyone to this day, like people who were in that class with me have been affected by him. And he's kind of really influenced the trajectory that a lot of us have taken. And I think this is just kind of how it goes. You know, you find someone that you click with for whatever reason, a teacher or a mentor, and you like working with them. And so you keep doing that. So Dr. Francis kind of got me into physics. And so I went to college and I was like, all right, I'll do engineering, you know, because that's sort of all, I didn't even know you could really be a scientist. I didn't know that was a thing. And then I noticed they were offering astronomy classes. I was like, all right, that sounds cool. And then I got linked up with a professor to do research. And that was really fun. And also, like, astronomy is pretty small. So, you know, the school I went to, there were like 20,000 undergrads. Whereas astronomy, I think there were like 4 people in my graduating class. And so it was a way for a big school to feel small. And also, like, if I'm being honest, you get some recognition because it's small, and that feels nice, right? And so I think just working with certain people who I found to be influential and I liked them, and they kind of made a mark on me that way. But I think it kind of could have been anything. It didn't, you know, there's nothing necessarily specific about astronomy. You know, if suppose I had an incredible literature teacher that I thought was, for whatever reason, I connected with, then that might have sent me down a different path. But yeah, generally, I think it doesn't really matter what you're into, but it's good to get into something.
Okay, any other last questions?
And I guess, like, the one last thing I'll say about that, now that I was thinking of it, like, I think it's almost worth taking a class solely based on the reputation of the teacher. It doesn't even matter what the subject is. So, like, if you know that this or that teacher is supposed to be incredible, even if you're not interested in what that topic is, to me, it's worth taking that class, because the vast majority of classes I've had, I've completely forgot everything I ever learned in these classes. But like, and that almost, you know, that kind of includes even when the teacher is very good. But like, when the teacher was very, very good, they leave an impression on you that counts for something. And so, yeah, that's what I'd say. I think, you know.
I think that's good advice. I think it's interesting. I think you have to try things. And I think that the path isn't always defined. So I think you gave some great examples, Greg, about, I mean, not having a telescope was a great example. I mean, if you've never had one, there are people that have them and they had them since they were little, but you will find your path along the way. And I appreciate your honesty and sort of going, I went to school, I could have been an engineer. I started as an engineering major. A lot of the coaches had other career paths. And we end up in education, and we end up in places that we have found our place, right? But we're still in love with science. I would say, like, our love is science, and we have a way to hopefully deliver and empower and bring interest. And that's something that's special about the NSSL for sure. Is another place to mentor and engage with our students in another way. So thanks for that honest feedback. And, you know, I have to say, I'm proud of my Masco students that are out there. We don't have astronomy at Masco. It's clear we have a lot of interest in some of this. So, you know, as somebody that might be able to influence things, it's interesting to see what they're interested in, because I'm a bio girl. So, but it doesn't make it not interesting. It's still very interesting.
Yeah, I mean, I didn't have astronomy in high school either, and a lot of astronomers didn't even have astronomy in college. The first time they ever took any astronomy, formal course was in graduate school, like after college. Yeah, and yeah, I don't know, if you find yourself interested in something and even if it doesn't quite align with the course, I think for the most part, teachers want to help you and be mentors, and they actually like working with students, and you're not going to bother them by like reaching out. And this goes for college too. Like if you're interested in the work a professor does, or you want to know more about that, like I'm telling you, I can't tell you the number of times I've sat in office hours and no one shows up, and it's just nice from the, I've only taught a little bit, but like teachers do want you to engage with them. And yeah, it's hard because there's a bit of like a hierarchy, and it can be hard to ask questions or to say you don't know things. And I don't know an easy way around that. But most people are nice, and they want to be a mentor, I think.